Hello and welcome to lesson 5.3. Today we're going to look at the part 1 video on electron configuration. Yesterday we talked about ground state electron configuration, and when we talked about something being at ground state, we talked about it being at the lowest energy level. So today we're going to kind of add to that, and we're going to talk about what we call electron configuration. Now the electron configuration tells us the arrangement of electrons in an atom. When we have a low energy system, these are going to produce a more stable system. Okay, and in nature, atoms they tend to try to arrange themselves in such a way that they are in the lowest energy level possible. And when they do that, this is what we call the ground state electron configuration. So the lowest energy level possible, again, is what every atom is trying to obtain. Okay, and this is what we call ground state electron configuration. So when we discuss ground state electron configuration, there's going to be 3 principles or rules that we look at. We have the Aufbau Principle, Pauli's Exclusion Principle, and Hund's Rule. And we're going to cover all 3 of those today. So the first principle we're going to look at is the Aufbau Principle. This principle tells us that the electrons are going to occupy the lowest energy orbital. And what we have here is we have an Aufbau diagram, okay? This is nothing you have to memorize. It does kind of show you in a quick glance kind of how the levels work and the sublevels work. I will show you an easier way between today and tomorrow as to how to figure this stuff out. But if you see a chart like this, you should at least understand how it works, okay? But ultimately what this does is this gives us a sequence of our energy sublevels. So notice our lowest sublevel is down here at 1s. So we're looking at this one down here. Then we're going to go from the 1s sublevel up to the 2s. And then from 2s, we're going to jump over to 2p, and we're going to fill that one. Then from the 2p, we'll go to 3s, then to 3p. Then we're going to go from 3p to 4s. And now this is where things change up a little bit. So we're going to go from 4s to 3d, 3d to 4p, then we jump up to 5s, and then the trend is just going to continue. Once we get up here to 5d, however, we are going to jump up to a 4f, then we're going to come back to do the 6p, then we'll do 7f, 6d, and 5p. So just so you can see, the S's are lower than the P's are lower than the D's are lower than the F's, and so on. Okay, so ultimately what you need to know is that there are 4 sublevels, and we did briefly talk about these yesterday, and those 4 sublevels are right here. These are something that you will need to know. We have sublevel S, P, D, and F. Now here what I have is I have a periodic table that kind of shows you where the S levels, the D levels, and the P levels all fall. Okay, with the exception of helium, because helium, we probably could, helium would kind of fit in right here. Okay, we'll talk about later why helium is over where it's at, but for right now, helium technically could fall here, so we could actually pull that all the way from over there to right here, and then that would fit right in with these first 2 columns. Notice the first 2 columns are always an S sublevel. When we get over into this region over here, these are our P sublevels. Our middle region, or our transition elements here, are the D sublevels, and these bottom 2, which is our lanthanide and actinide series, these are what we call our F sublevels. So I'm going to use this periodic table a little bit in some of our kind of class discussions here, and then you are going to be responsible for knowing this stuff come time to take a test. They're not labeled like this on the orange periodic tables that we use on testing quizzes, so I would suggest that you kind of start to memorize them, and I will show you easy tricks to kind of help you remember that too. But just so you can see, again, we have our S's in the first 2 columns, P's are going to be over here, D's are always in this middle region, and the F's are these 2 bottom rows. Now the other thing that you can notice is with the S and the P's, notice this is row 1. So row 1, I have 1S and 1S. Row 2 is 2S and 2P levels. I have my third row is 3S and 3P. For the fourth row, we have 4S and 4P. Now notice our middle blocks here though. These are going to be one row less than the row that you are actually in. So technically on my periodic table, if I label these, this is row 1, row 2, row 3, row 4, 5, 6, and 7. And if you notice, in row 4, my D levels are actually a 3. In row 5, my D levels are actually a 4. And that trend will carry through with all 4 of these. Now the F's, okay, are actually going to be 2 rows off, because technically this row right here is going to fit kind of like in here, while this bottom row here would fit in right here. So if you notice, this is my 6th row here, and the 6th row is the 5th D level, but it's actually the 4th F level. Likewise, for my 7th row, I have 7S and 7P if we had P elements. That would be 6D because it's 1 less, and then when I come down here, it's actually 5 because my F levels are 2 rows off. And again, we'll talk more about this. Next, we have what we call Pauli's exclusion. Pauli's exclusion says that electrons and orbitals are represented by arrows in boxes. So as you can see here, I have some boxes drawn, and if we want to go and we were to draw in some arrows, I could draw them in something like this, and you can see that I have 2 electrons in that box. Now as we continue, it says each electron has an associated spin like a top, and it says you can only spin in one of 2 directions, and we are going to show our arrows having spin by pointing one arrow either upwards or one downward to represent spin. So you could either draw 2 arrows that look like this, or in a lot of text series or scientific things, you're going to see that they'll show it with the outside edges of the arrows only, and that's because it makes it easier to fit in that box. I don't care which method you use, but just know that you may see it shown something like this here, and that really means the same thing as this. Okay, and one other thing to point out here is if you see that you have arrows in multiple boxes, okay, each arrow, remember, represents an electron. So if I go and I count these, like here, this has 1, 2, 3, 4, 5, 6, 7 arrows. So if I come to my periodic table, this is actually the element nitrogen, because nitrogen has 7 protons, which means it most likely has 7 electrons. So just by counting the arrows, I can figure out which element we're dealing with. Now Pauli's exclusion also tells us that each empty box indicates that we have an unoccupied orbital, so it just means that nothing's hanging out there. A box that has 1 arrow tells us that there's only 1 electron in that box. And then it says a box with an arrow up and down means that that orbital is full. So again, if I come in here and I draw something like this, that tells me that this orbital is full because I have 2 electrons. Something like this means that that orbital only has 1. And then when we look at these 3 boxes here, this orbital is empty because there are no arrows drawn in there. Now one thing that you have to keep note of, and that's this right here, where it says a max of 2 arrows can occupy a box, okay? And they must have opposite spin. So you'll never put any more than 2 arrows in a box, okay? And you can never have something like this. They must go in opposite directions. I don't care if you draw something like this, or if you start out going down first and then up, okay? Me personally, I tend to do it like this just because I think it's easier. Now, just to kind of jump ahead a little bit, and we'll talk more about this tomorrow, but if we want to do an element, let's say we want to do something like, let's go to boron. Boron is element 5 right here. So what I'm going to do is for each box that I encounter, I'm going to drop an arrow with each element that I encounter off the periodic table, I'm going to drop an arrow in each box. So hydrogen, I'm going to cross hydrogen off. That gives me 1 electron. When I do helium, that gives me 2 electrons. Then I'm going to come over here to lithium, which is 3. So now, if I were to stop right here, I could say I've got 1, 2, 3 arrows, which tells me I'm on my 3rd element, or lithium. If I want to continue, I have beryllium, so my arrow would go down here. And now notice I'm over here into my P levels. So this right here is my 1s, because notice that was helium and hydrogen. This here is my 2s, which are these 2 elements. And now I'm going to hit this row right here, which is going to be my P's. So this is my 2nd row in my P elements. So for boron, which is right here, I would draw an up arrow. Then I have carbon, would be another up arrow. Nitrogen would be another up arrow, because now I'm at 2, 4, 5, 6, 7 electrons, which is what nitrogen is. Then for oxygen, I'm going to switch my spin and start going down. Fluorine would be right here. And notice when I hit the end of my row, I now have all of my boxes are full. So in this case, I have my 1s sublevels full, the 2s sublevel is full, and the 2p sublevel is full. Okay, and again, just by looking at this diagram here, notice I have 2 arrows in my 1s, 2 arrows in my 2s, and 1 arrow in each of the p level boxes. So this tells me I have 2, 4, 5, 6, 7 electrons. So 7 electrons tells me that I have the element nitrogen, which again is indicated down here. Now the last rule we're going to talk about today is called Hund's rule. Hund's rule states that a single electron with the same spin must occupy each equal energy orbital before additional electrons with opposite spins can occupy the same orbital. So the example I like to use for this is I like you guys to think about yourself when you ride a bus, okay? Typically, when you get on a bus, you're going to go and try to find an empty seat. And it isn't usually until all the seats are filled up before you start doubling up. So that's the same thing with electrons, okay? So when I look at my 1s level here, hydrogen's going to come in and fill in that first seat. Well, because this is my 1s sublevel, first row S sublevel, helium is going to be forced to have to sit with hydrogen because it has to fill that S sublevel first. Now when I come down into my 2nd sublevel, okay, so I'm going to be right here. This is going to be my 2s sublevel. Lithium's going to sit down here first. Then beryllium's going to be forced again to come in here and sit with lithium because there's no other seats available in the S sublevel. However, when I jump over here into my 2p, or my 2nd row P sublevel, boron's going to come fill the first seat. Then carbon's going to get its own seat, and nitrogen will get its own seat. So boron, carbon, nitrogen. When oxygen comes along, oxygen is now forced to have to pair up with another element. So oxygen will pair up, then fluorine is going to pair up, and neon will pair up. So now I have my 1st and 2nd row elements accounted for. So let's go ahead and do the 3rd row. Okay, so I'm going to start out. These are my 3s sublevels. Let me change my color here. We'll go to green. So our 3s is right here. So sodium, or Na, is going to fill the first one. Then magnesium is going to come along and be forced to sit with sodium. Then I'm going to jump over here, and aluminum will fill in first. Then silicon gets its own seat, and then phosphorus will get its own seat. And now I've got aluminum, silicon, phosphorus. Now sulfur is going to be forced to have to start pairing up. then chlorine, and then argon. So that gets me these 3 elements right here. And this is my 3rd row in the P sublevel. We're going to stop right here for today. Please let me know if you have questions on this stuff, and we'll continue on with it tomorrow. Have a great day.